Okay, so we're going to take a look at something that we've looked at in class for APC, center of mass. Specifically, we're going to find the center of mass of a continuous and uniform object. Specifically, we are going to take a look at using the following equation that the position of our center of mass will be equal to 1 over the total mass of the integral of x dm. This is our equation for the position of the center of mass, and we're going to apply it onto a nice uniform object here. This is a wooden, triangle. You could imagine it's a type of wedge, although it's not a right triangle, it's actually an isosceles triangle. So it's flat here and it goes out evenly on both sides. You could imagine a line straight along here and we'd have a right triangle up here and a right triangle down here. We could call this a triangular prism. So here's what we're going to do. It's going to be a lot like this. I'm going to give you some dimensions here. I'm going to say that this has a total length of h. Why do I say h? Because I'm used to thinking about it like this, where that's the height of it. I'm also going to say that we have a total length here of L. Now, when I look at this, I've got some angle that it goes out at here, theta. Now, theta is going to remain constant as this, because it's an angle. I could measure it. It's not like it changes partway through with this straight line. Now that's going to be parts of what we need. We also have this go back into the board with some thickness I'm going to call T. Thickness is going to be this. It's kind of the width. Okay, so we're looking at it like this. It goes back into the board. And what I'd like to know is, at least in this dimension, so here, if I look at it like this, I know that side to side here, my center of mass is going to be pretty much in the dead center. I'm also going to find that here, same thing, those two are probably going to be directly in the center. The big thing that I need is this. If it's on its side like this, I can't just put it in the center here because it falls over. I'd like to know where along this length is my center of mass. Now, we can predict that it's probably going to be closer to this end because that's where more of the mass is. But let's see if we can do more than just guess. Let's see if we can actually predict it fully. So this is what we're working with, triangular prism, and this is me setting up some of the materials. Now, this is made out of wood, and we're going to say that it's nice uniform wood with a constant density of rho. Now, this is a volume density. The example that we did in class was a linear mass density that we used with a meter stick. I'm going to show you how to use the full volume, and what we do here is directly applicable to what we did in class. All right, here's what we're going to need, though. What I need is the following. We're going to go from x. We're going to say x starts here at x equals 0, and it goes all along here in a straight line until we get out here, where x equals h. So I'm going to integrate from x equals 0 to x equals h. And what I'm trying to do is this. Once again, with this setup, we're saying that the center of mass, we saw it before where when we had objects in class, we have an object here and we have an object here, and we would find their center of mass by taking the mass times its location plus the mass times its location, and then we'd add all of those together and divide it by the total mass, and we'd find in this case that it was pretty much directly between the two. For the not equal, we saw that we had a heavy mass here and a light mass here. In fact, it might be better representation if I put it like this. And we solved this in class, and we found that the center of mass would be pretty close to here, and we could get it to balance. Now, that was using discrete things. Now, what we want to do is we want to do something similar with something that is continuous. And what we're saying is, at some distance x, I'm going to draw this out, we're going to do a little blue one here. At some distance x, there exists a small strip, an infinitely thin strip, at point x, and it has an infinitely small mass. Now, what I want you to do is I want you to imagine this. Instead of having one solid object, we can pretend it's a lot like these objects, where we've got an object here, an object here, object here, object here, object here, and so forth. But what we need to do that is we need to imagine that you're cutting this up like a loaf of bread, and we're cutting it into little strips. Now, each of these strips is going to be infinitely thin because I don't have just one block here and then one block here and one block here. I have one that's immediately connected right next to the next one. And so what I'm going to do is I'm going to imagine this solid object as nothing more than an infinite number of little window panes. And why do I say window panes? I want you to imagine that we're looking at it from the back side here or the front side, either way. If we did a cut, what we would be looking at would be something that goes into the triangle, back out like this, where this is the thickness T, and it's going into the board. If we were to look at a cross-section of this, it would look a lot like this. So if I were to slice this into bread and take out one little slice of bread, it would be like this, where it kind of goes back into the board. Now I'm going to look at it from the side, where I see it like this. Now, I need to try and find out the volume of this bread, because what I really need is I need the mass of this little tiny piece of bread, and since it's infinitely thin, it's going to be an infinitely small piece of the mass. At position X, we have an infinitely thin slice of bread that has a mass that is so small that it is an infinitely small piece of mass. And once we get that set up, we can integrate, which is adding up all of those little slices until we add all of them up to be the solid object. That's what this is doing. Now, our problem is our position changes depending on which piece of bread we're looking at, and the amount of mass that we have also changes because the pieces of bread get bigger as we get farther away here. So we need to relate those two things. And how we can do that is with the density. We can get the following. Here's what I want to do. I want you to imagine that our piece of bread is like this. It has some thickness, some width, I should say, of dx. It's an infinitely thin little strip, but it has a thickness of dx, okay? And that's this part right here. It goes back into the board by a distance t, and it has a height of, well, that's where it's going to get a little bit tricky. We know that this is going to be y. So here's what I'm going to do. I'm going to draw this out in red. Let's say that we're looking at this slice of bread right here, somewhere involved here. We've got a y that looks like this, and we've got an x that looks like this. All right. Now, as we continue in x, y gets bigger, but they're not the same thing, so we're going to have to set up how they're related to each other. I can say this, that since we've got the infinitely thin slice of bread, it has a thickness of dx, it has a width going into the board of t, and it's got a height of y. If you imagine it as a tiny slice of bread, then our volume of that slice of bread is going to be base, t, times height, y, times thickness, dx. Sorry to interrupt. I'm going to splice this in the middle of what we were doing, but I can't believe I didn't think about it at the time. I was probably in too much of a hurry. Sorry. But instead of thinking it, well, many of you may be thinking in terms of what we want, which is with the large prism, we were cutting it into slices that were like bread. But to make it where it's got a nice smooth edge on top and on bottom, they have to be infinitely thin slices of bread. So real quick, best way of thinking about it would be a piece of paper. So this would be part of it, and then the next one over here would be a slightly longer sheet of paper, and a longer sheet of paper, and a longer, and back over here we'd have a shorter and shorter and shorter until we got down to something that is incredibly short. But what I'm talking about with the volume is I want you to think of this piece of paper not as an infinitely thin sheet, even though that's more or less what we're dealing with. It's not actually infinitely thin, but it's a good way of thinking about it. But as kind of a slab, a block. So you get a whole bunch of papers together, and they make basically a rectangular prism, a box. And the volume of that would be this times the thickness here. Well, the same thing applies to the infinitely thin little sheet of paper. We would have, here's our block, we've got this times an infinitely thin piece. This is the dx, the infinitely thin little strip, and we're going to multiply it by this, and that would give us the volume the exact same way as having something that is finite thickness. We'd multiply this times this, and it would give us the volume of the full thing. All right, so I'm going to cut this in the middle of the other video where I'm talking about finding the volume of that infinitely thin little slice of bread. But just so you've got a way of imagining it, for our purposes, we have that this length is y, this is t, and this is dx, an infinitely thin little piece of x. Now, t is great because t is just the thickness of this, how wide this is. That's just a number, it's a constant, it stays the same. Our big problem is y changes. So we need to put y in terms of x. I'm going to draw this out. We've got a triangle that looks like this. With theta here, we've got x here, and I'm going to call this y over 2, because we know that it goes down here, and the other half of y is down here. We've also got, if I were to draw this out, h comes out over to here, and we've got L divided by 2. Now here's the thing, what's actually constant about these is the angle theta, but I can set up the following, that if I have tan theta, which is a constant, because that angle does not change, and taking the tangent of a constant is still going to give you the same number each time. Tangent is TOA, opposite over adjacent, so that gives me y over 2 divided by x, or I could also write this as y over 2x. But that's for the red triangle. We also see that theta is also in the green triangle, and that tangent theta of that is going to be equal to opposite L over 2 over divided by the adjacent, which is h. We find that tan theta is also equal to L divided by 2h. And since tan theta in both cases are the same, we get the following relationship, that y over 2x is equal to L over 2h. Why is this useful? I multiply this over and we get the following relationship, that y is equal to Lx divided by h. The 2's will cancel out. I'm going to multiply by 2x, 2's cancel out. That disappears, and now we have y equals that. Why is that useful? Let's go back up. Remember how I said that y changes if we change x? And since we're integrating with respect to our length, we're going to go across x. We need to express y in terms of x, which is exactly what we get. This tells me that if I take one of those little tiny slices of bread, as it were, that the volume, the infinitely small piece of volume, I could say, is going to be equal to, well, we had the thickness of it, t, times y, the height of it, which we said, y, yes, y. Y equals Lx divided by h, times the width of it, which is dx. This is my volume. So if I want to find the infinitely small mass, I can deal with the following. We talked about this in class, that the density is equal to the total mass divided by the volume, but we're also going to find that the density will be equal to an infinitely small piece of the mass divided by an infinitely small piece of the volume. Well, this is the volume of my infinitely small piece of bread. So if I take this volume and I multiply it by the density, rho dV, my density times the volume of that tiny little piece of bread made of wood, and the density of that wood times the volume will get me the mass of that infinitely small piece of bread. I'm going to double check my recording real quick, think that over. All right, still looking good. I'm trying to go through this quickly. I think my phone is about out of space, so I'm trying to get this done pretty quickly. What this allows us to do is we now know with this relationship that dm is equal to rho times dv, and we just did a lot of work to find that dv is equal to t times lx over h dx. Why is this useful? Because the center of mass will be at 1 over m times the integral from 0 to h, the full length that we're going to integrate, of, we said x dm, our position of that infinitely small piece of mass times whatever that infinitely small piece of mass is, the little piece of bread that we're looking at. So now we can rewrite this because we now know that dm for this problem can be expressed as rho, the density of the wood, times t times Lx over h times dx. Rho is a constant, t is a constant, L is a constant. The length here is a constant, and h is a constant because we're dealing with a real-life physical object. In short, everything here is a constant except for x, and dx, which means I can now write this as the following. The center of mass is located at, I'm going to do rho t L over mh. I pulled rho out, I pulled t out, I pulled L out, and I pulled the divided by h out, times the integral from 0 to h of x times x, which is x squared, dx. Now this is a lot of work to set up. Once you get it set up, that's the hard part. It actually gets really easy. We know that our center of mass will then be rho times TL divided by mh of, I'm going to integrate this, I get 1/3 x cubed evaluated from 0 to h. The lower limit of integration is just 0 and that disappears, so we end up with x, the position of our center of mass is rho TL over mh 1/3 h cubed. Well, we've got an h here and an h here, so I'm going to remove the cubed and we're going to go down to squared. And here's where we do a little bit more on this. Let's see, we've got 1/2. Wake up, Sanchez. 1/3, I apologize, 1/3 h cubed. One of the h's cancels out. And then we get the following. Let's see. I've got to clean this up just a little bit more. X, let's see, equals our density. Let's do something with the density. Real quick, I told you that the density was going to be equal to the total mass of this thing times divided by the total volume. Well, that's going to be the mass divided by the total volume of this thing, which, well, the top, let's find the volume of this total thing. We're going to have some height, t, times the area here, this triangle. So we know that that's going to be 1/2 h times L, base times height. 1/2 of that will get me the area of the triangle. Then I multiply it by the depth here, t, and that will be equal to our volume. So I can put this in up here and we get 1/2 HLT is going to be our volume. So my density is equal to the mass divided by 1/2 HLT. I can now plug that back in up here. Hopefully my camera's still going or else this is going to be a little weird. So now that I've got that, we've got rho TL, so I'm going to do x center of mass. We know that it was rho, which is going to be 1/2 TH, not rho. So rho is going to be equal to m divided by 1/2 THL, so that's going to be rho, times, I'm going to put rho off by itself. Here's rho, I wrote that out. We're going to have TL divided by m, TL divided by m, the total mass, and the h got canceled out here. We have 1/3 h squared, 1/3 h squared. All of these are multiplied. Let's see, L cancels out with L, M cancels out with M, T cancels out with T. One of the H's cancels out with that squared there. Wow, we got a lot that actually got worked out, and we find the following. There's a 1/2 down here. Our center of mass, the way that I've got this set up, the 2 flips up there, we end up with 2/3 H. If X is 2/3 H, we come back up to where we started, and that means that we want, if this is 0, this is H, then we'd need 2/3 of the way. It's right in here. Let me double check my recording. Great. We got all that important stuff. Here's the last thing that I'm going to do. I actually measured this out before. This has a total height, h, of 10.2 centimeters. When I did the math on that, dividing it into thirds, that gives me that this distance is a certain amount. I just used the 1/3 here, which was, I think, 3.4 centimeters. I've actually marked it out, and I put a little dot there. Here's what I'm going to do. I'm going to try and put that dot right in the center on this peg, and we get the following. There's your center of mass. 1/3 of the way from the far edge, 2/3 of the way from the pointy edge, which is exactly what we predicted with this. Now remember, this would be in the center here and in the center here, but for this part, it will be 1/3 of the way in, which is what I've got marked. And we have it balanced. There we go, center of mass.